Let's get some practice computing the mass of a system from its density, size, and shape. In this example, we'll consider a cylindrical pipe filled with some sort of gas. We don't really care what. And here are the dimensions of the pipe. I'll define the positive z direction to be pointed upward. The challenging part is that the density is not constant. If the density were constant, we would just compute the volume of the cylinder, relatively easy to do. Multiply that by the density, that would tell us the total mass of gas in the pipe. The problem is this particular system doesn't have a constant density. So let's assume that the density is in fact a function of height, and more specifically an exponential function, where the constant rho naught tells you the density at the base of the pipe, and this other constant z naught, often called the scale height, tells you the distance over which the density varies by a factor of e. Okay, now we're obviously going to have to do an integral because this is not a constant density, so let's set everything up. The total mass of gas in the pipe is going to be the volume integral of density times dV, where dV is the differential volume element. Now, our goal in a problem like this, seeing that the density only depends upon one spatial dimension, is to convert this to a 1D integral. Honestly, one of your goals in life should be to convert 3D integrals into 1D integrals that maybe you actually have a chance of doing. So let's split this into a part that depends upon the area, the cross-sectional area, and a part that depends upon z. So if we do that, you can see that the nice thing is this first bit here, the integral of dA, that's just going to be the cross-sectional area of the cylinder, which is actually just the area of a circle. The second part is the definite integral in z, and that's the part that we'll actually have to integrate. But it shouldn't be too bad. So if we rewrite this as mass equals area times that definite integral, and we put in the form of the density, now we see that we just have to integrate an exponential function. So I'll pull out some constants, and we're going to have to do a substitution. You might be able to do this one in your head, but just in case, let's come up with a dummy variable mu, and make sure that we remember how to actually do the differentials properly. Now, if we make the substitution on a definite integral, we need to change the limits of integration too, so don't forget about that. And now we get this expression, where the limits of integration reflect our substitution. But now the nice thing is, especially if we pull out that z naught constant, we just have an integral of an exponential function. Alright, everybody knows, the great thing about exponentials, although they're a pain in other ways, is that the integral of an exponential is an exponential. So let's look at the two limits here, and remembering that the exponential of 0 is not 0, it's 1, and we'll put that minus sign back in, we get this expression here. So we're now in a position where we could actually go in and insert values for rho naught and z naught, remembering that in this case, h has to be 1.5 meters, right? Because we said that the base was at 0. So we put all that stuff in, and now we just need to multiply it all out. We get that the mass of gas inside this pipe is 1.85 kilograms. Now, it's never a bad idea in a problem like this to do a sanity check. If we had had a constant density of 2.00 kilograms per cubic meter, then actually the mass would have come out to be about 2.4 kilograms. So indeed, we would expect a value that's smaller than that since we have this exponential density, meaning that overall the average density is less than the density at the base. So this problem serves as a good illustration of a method for converting what could look like a complicated 3D integral into a fairly straightforward 1D integral that we can handle without too much trouble.